let's recap on what we covered last week. Okay, that was a long time ago, it feels like. We introduced acids and bases, and we talked about how to define an acid and a base. We said an acid is a proton. I think there's like a recap slide right up here. Maybe it's further up than I thought. Okay, an acid donates a hydrogen ion and a base accepts it. So we call the acid the proton donor and the base the proton acceptor. That's the nicknames we gave them. We looked at several examples of acids giving away the hydrogen ion and bases receiving them, and how those elements change charge. So if they're neutral and you're a base and you accept a hydrogen ion, you become positive. Okay, that's this example right here. And if you are negative as a base and you accept a hydrogen ion, you become neutral. That was the bottom example. We redefined an acid-base reaction. Instead of just one that makes water as a product, we said it's a reaction in which a proton is transferred. That's a more general definition. You can have an acid-base reaction even if you're not making water, but you just have to make sure a hydrogen ion is transferred. And then we practiced identifying those. We talked about conjugates. Okay, and we said when an acid-base reaction occurs, the result is a weaker acid and base. And we learned how to label, identify acid-base conjugate pairs. Practice writing those out. And then we got into acid-base strength. And what we talked about there is we said strong acids dissociate 100%, single arrow pointing to the products. Weak acids dissociate a portion, okay, not fully, not 100%. It could be very little, it could be relatively a lot, just not entirely. So that's why we put a double arrow in these reactions. And with those, we can have an equilibrium set up, because these products can reform together and remake your initial acid and base. And then we approach that strength of bases as well. I gave you this resource, the table is in your textbook, and we talked through different sides of it. And now we're going to really dive into weak acids. Okay, so weak acids, I'm going to turn this sideways so you can see a little better. Okay, because the dissociation of a weak acid is an equilibrium, double arrow, we can write an equilibrium equation. And I'll let you pick the emoji that describes how you best feel about equilibriums. Okay, I know most of you will pick this one. Okay, and very few of you will pick that one. So weak acids, remember we abbreviate acids HA. Let's actually write out an equilibrium expression for a general weak acid. Any weak acid, acetic acid, and we could go up to this table. In any of these weak acids, remember we can write an equilibrium for. So it doesn't matter which one, we're just going to call acid HA. And let's say we have water here. And when these two react, you get H3O plus the hydronium ion and the conjugate base of the weak acid. So remember, K is the concentration of products over the concentration of reactants. And we raise them to the power of their coefficient. Here, our coefficients are all just 1. But remember, if you do have coefficients, you plug those in as an exponent on the atom it is connected to. So if we're writing it for this, let's put in our products. Well, it'll be the concentration of H3O plus hydronium ion times the conjugate base. This is our conjugate base. And that will be over the concentration, the original concentration of the weak acid times the concentration of water. Okay. Now, there is a minor difference between an equilibrium expression for a weak acid and just for a typical chemical reaction. And here is the difference. Here's the modification we're going to make from regular old K. So I'm just going to read these points through. Even though water is a reactant, it's also the solvent. Okay, remember we said all acid-base reactions occur in water. So because it's the solvent, the concentration of water is ginormous. Okay, it's insanely large. It's insanely greater than any other reactant or product in the equation. And because of that, the concentration of water is not significantly affected when the acid dissociates. If we plugged in the concentration of water into this equation, it would dominate all other numbers, and essentially our K would be 0 every single time, and we would not learn anything meaningful from K. So to actually have something meaningful come out of K, we just remove water from the equation. All right, we're just going to take water out. We're going to multiply by both sides. We're going to remove it from this side of the equation. So we group water with K and we'll write, we'll call these together. We'll call this Ka, okay? We call that the acid dissociation constant, Ka. So here's the new form down here. I'm gonna let you guys finish writing up here. Make sure you have this equation down, but we'll clean it up and we'll see what the final version is. This is Ka. Ka is actually K times the concentration of water, but here's what it equals. Hydronium times the conjugate base divided by the weak acid, okay? Hydronium ion times the conjugate base, concentration of that, divided by the concentration of the weak acid, okay? At equilibrium. Okay, concentrations at equilibrium. All right, so this is Ka. This is the equilibrium expression for a weak acid. Now I'm going to follow this up with the question, why don't we write them for a strong acid? I better pull my chat up. I forget to do that. Come on. Why do we not write Ka for a strong acid? Anybody? Because water would be affected, because water is less dominant, because it will produce all products. There we go. Thank you, Abby. Remember, strong acids, we don't have an equilibrium. Strong acid, if this is a strong acid, plus water, we just have a single arrow. And A minus, we get all products, okay? We don't have the double arrow. So if we don't have a double arrow, we don't have an equilibrium and we don't have Ka. This is just for weak acids. I want to drive that point home, just for weak acids. Okay. So continuing, we're going to see how K tells us important information. Why is K useful? Why do we care, or Ka, I should say. So here's our equation for Ka, the one we just kind of derived. And here's a chemical reaction for the dissociation of a weak acid. What does Ka tell us? Ka directly tells us about the strength of the acid. Now remember, this is not if it's a strong acid or not. This is just when you have weak acids, you still have a scale, okay? You can have an insanely weak acid, like the weakest of the weak, or you can have a relatively decent acid, but is still considered a weak acid, okay? So we're just talking about on a spectrum of weak acids here. How strong is that weak acid? And I should honestly say that, of the weak acid. So the larger Ka is, the more that your product is favored, right? So if these are products, and this is reactants or reactant, the larger your numerator is, the larger Ka will be, okay? The larger the top part. We can't see what you are writing. Well, thank you for telling me. Sometimes if I stop share and reshare, that will fix it. Oh, I was doing this yesterday. Okay, got it. Okay, now can you guys see that? All right. So we said Ka directly tells us about the strength of the weak acid. And the larger Ka is, the more products you have. And numerically, that makes sense. If we have, I don't have my pencil on. Ka equals 10 divided by 1 versus, I should say, Ka equals 10 divided by 5, okay? Well, that's actually a bad example. We should say 100 divided by 1. Okay, the larger your products are, the larger that top number is, the larger Ka will be, right? 10 divided by 1 is going to give you a value of 10. 100 divided by 1 is going to give you a value of 100. So the more products you have, the larger your Ka value is. Now the product is the dissociation. So the larger the Ka, that means the more dissociation you have. Okay, this is the dissociated side of this reaction up here. Acid in its dissociated form. And the more the acid dissociates, the stronger it is. Remember, we said, would you rather, last week I said, would you rather ingest or drink, a small amount of HCl, hydrochloric acid, which is an insanely strong acid, or a small amount of vinegar, which is acetic acid? And we know HCl is highly corrosive. Why? Because it's a super strong acid. Why is it a strong acid? Because it 100% disassociates. So the more an acid disassociates, the stronger it is, the more corrosive its effects are. So what we're trying to say is the larger Ka equals the stronger the acid. And remember, we're still only talking about weak acids, not strong acids. Okay, we're on a spectrum here of weak acids. Questions with this. The larger Ka is, the stronger your weak acid is. The smaller it is, the more weak it is, and the less it will dissociate. So I'm going to show you another table, and you'll have this table as well on your resources page for exam 4, and it's in your textbook. This is a table of Ka values that correspond to different weak acids, okay? So if I were to have you look at this table here, which acid on this table, these are all weak acids, but which one's the strongest and which one is the weakest? If you're looking at these values, we have all kinds of, a whole range, some with 10 to the minus 4, some with 10 to the minus 2, some with 10 to the minus 13, 10 to the minus 11. Oh, people are typing in the chat. Let me pull that up. Okay, HSO4 is the strongest. This one right here is what? Well, this says large, so I bet that one, yeah. H2SO4 doesn't even give us the value of that. And I want to say that might be grouped. It's really deceptive if it's grouped with the strong acids. Sorry, let me scroll back up. Yeah, I don't even know why that's on there. Sulfuric acid, look, it's grouped as a strong acid. So I think it might just be on there to show you it's the predecessor of HSO4 minus. Okay, so this one is actually not a weak acid. This is a strong acid. But right beneath it, HSO4 minus is still an acid. And of the acids on this table, it has the largest Ka value. It's only 10 to the minus 2, which is still a small number. But compared to the other relative, it's the highest one on here. So this is the strongest weak acid. And which one would be the weakest weak acid? The last weak acid that will be picked for the wiffle ball game on the teams. The weakest one. HCO3. Okay, where's HCO3? HCO3. Okay, Jenna says this one right here. Jenna said I lied. Jenna, come on now. Which one is the smallest? HPO4 with a minus 2 charge. You're right. This one is even smaller. The Ka value is 10 to the minus 13. Okay, so that is the weakest. All right. So that's a little bit about how to read this table. I want you to get comfortable with using this table. We'll do some practice problems and for sure on the review. By the way, Monday, the day before the exam, will be a day full of review. So we'll work some weak acid practice problems and I'll try to make sure those are on your homework as well. But anyways, so that's enough about weak acids, and we will later try to work a weak acid problem. Okay, so we'll come back to weak acids, but we need to move on and talk about water. Okay, we've said water is in all acid-base reactions, and the unique thing, we've already seen this with water. Water can act as both an acid and a base. All right. So when we put water with a base, a chemical compound or molecule that is a stronger base than water, water inherently default plays the role of the acid. And what that would look like, if it is going to give away, I should draw the arrow the other way because we always draw it from the lone pair on the base. It's going to grab off a hydrogen from water, and it will make H, whoops, I'm all over the place today, NH4+, and it will give us OH-. Okay. And then, so that's water acting as the acid. It gives a hydrogen away. Water acting as a base, it is going, we've got lone pairs on this oxygen. It's going to grab the hydrogen off of HCl, who gladly gives it. This is a strong acid, so single arrow here. And we're going to have H3O+ is our product and Cl-. So there's proof water can do both, if you remember. Now, what's even more awkward or weird about water, it's almost as though if water were a person, it has like multiple personality disorder, okay? If you have that, don't tell me. But if you know someone who has that, it's a real thing. Water can act as both an acid and a base with itself, okay? So that's weird. Let's just say this one is the base, and let's just say this one's going to be the acid. So we've got lone pairs here. It's going to grab the hydrogen off the neighboring water. And this is a very weak acid and a very weak base. So we definitely have equilibrium set up here. And what are we going to get? We're going to get H3O+ and OH-, hydronium and hydroxide. And if anybody has twins in their future down the road, there's a set of twin names for you, hydronium and hydroxide. All right, now this happens to a small extent in all aqueous solutions, right? All aqueous solutions. So essentially every aqueous solution has some concentration of some amount of H3O+ and OH-. It's present in all solutions to a very small degree. All right. And because it's an equilibrium setup, guess what? We can write a K equilibrium expression for this very reaction right here, which is unique only to water. We can only write this for water. So we take the products, H3O+ and OH-, and we're going to put those in right there, concentrations on top. And we have two water molecules, so we just say water squared. That would be as if we have two H2O, okay? So we say water squared on bottom. Now, just like the modification we made for the Ka equilibrium expression, we're going to take water out here for the same reason. Water is just, it's the dominant molecule. We only have very small amounts of our product. So if we want to understand what's happening with product concentrations, we need to remove water. We remove the concentration of water. So we write what is called the ion product constant. Okay, why do we call it this big long name for water? Well, these are both ions, right? This one's the cation and this one's the anion, and we're multiplying them. And when you multiply something, it's called you product, and K is going to be a constant. So the ion product constant for water, and we put a little W there to remind us, oh, we're talking about water here. So Kw, once we remove water, both of them, from the denominator, we just have this, H3O+ times OH-. And I'm going somewhere with this, so hang tight, we're almost there. This is Kw, say, okay? So remember, any equilibrium expression you write specifically for an acid-base reaction, it's different than any other equilibrium expression. You always take water out, okay? Water sits the bench. Now, as a reminder, we have Ka and Kw. How are they different? But how are they the same? Well, they're the same because we remove water from both. But how are they different? That's how they're the same. How are they different? Well, Ka is going to be the concentration of H3O+ times the concentration of the conjugate base over the concentration of the weak acid, Ha. Okay. Now, one thing I want you to remember, when we started this whole lecture, I introduced the definition of an acid. I said, remember that we use H3O+. We say that's synonymous with just H+, hydrogen ion. Okay, so this right here is essentially just like if we have H plus. So if I ever ask you, and this is going to be important for the slides coming when we talk about pH, if I ask you to find pH and you have a concentration of H3O plus, that's the same as concentration of H plus. Just remember that, because H plus is what affects our pH, which we're getting to. Just remember this right here. These two are synonymous, okay? The concentration of H3O plus is just like you're saying concentration of H plus. All right, enough on that. Kw is different. It is just the concentration of OH minus, no denominator here. Hydronium and hydroxide. All right, that's how they're different. And this one is just for water. Pure water only. All right. Now we actually have a value. It's a constant, so it does not change. We have a value, a numerical value we can plug in for Kw. And it's known and it's set, does not change. It is this: at 25 degrees Celsius, Kw equals 1 times 10 to the negative 14. Very, 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 very small number. And that makes sense because water is not a strong acid or a strong base. It's like the weakest acid and the weakest base ever. So if we plug in Kw to our equation, now we have this: 1 times 10 to the negative 14 equals concentration of H3O plus and the concentration of OH minus. So that's if we plug in Kw, which you can always do. You can always plug in this value for Kw. It equals the concentration of H3O plus times the concentration of OH minus. Now, in pure water, nothing else is there, just water molecules doing what we saw earlier. I'm going to scroll back. I'll be right back, but I'm going to scroll back up, doing this right here, this reaction. Nothing else is there. Every time one water molecule gives away a hydrogen, one water molecule accepts it, we make one each, one hydronium and one hydroxide, okay? So the concentrations of these two things, hydronium and hydroxide, they're going to be the same. You can't make one without the other, okay? They're identical. So what that means is that their concentrations are a value we can determine. It's essentially like saying this: 1 times 10 to the minus 14. If we just plug in X for both of these, and we can plug in X for both because they're the same, the concentrations are identical. So that's like saying this equals X squared, right? X times X is X squared. So now we can solve for X. We just take the square root of both sides. So what is X? X equals 1 times 10 to the minus 7. And it is units of molarity, moles per liter. So guess what? The concentrations, well, I meant to do all that work down here, but the concentrations of H3O plus and the concentration of OH minus, they're both equal to 1 times 10 to the minus 7. And this is in pure water, okay? Pure water. Oh, Allison, I'm not sure when you sent that. You want me to, where do you want me to scroll up to? Sorry, I was not paying attention to the chat. Do I still need to scroll up? It's fine. Okay. Sorry. All right. So what's the point of all this? Well, we're actually going to start putting this into some practice problems and seeing how this helps us. We're building up to learn about pH, which is a big, big deal. So we're going to do a practice problem with Kw. Okay. What are the concentrations of hydrogen ions and hydroxide ions? Okay. So hydrogen ions, remember, this is like saying H plus, that's a hydrogen ion, or which is the same as H3O plus. And hydroxide, which is just the OH minus. So what are the concentrations of these things if we have a 0.1 molar solution of hydrochloric acid? Well, how in the world do we find this out? Well, let's think about HCl for a second. What kind of an acid is HCl? Anybody remember? I said you didn't have to memorize these, but HCl is actually a pretty popular one. It's a very strong acid. And remember what strong acids do? Let's just write that out. What does a strong acid do? What is it going to give us? Just write the dissociation reaction for HCl. You should just have H plus and Cl minus. when it disassociates. So if we have 0.1 molar of this starting out, we have 0 of these. So this is our initial, put an I there for initial. What's our final? We should end up with 0 of this, 0 HCl, and 0.1 molar of this, and 0.1 molar of that, right? If all of it, every molecule, every bit of it, and we didn't change the volume of our solution, so our molarity is just going to be what our products are. So guess what? We have just found the concentration of H plus. So we already answered that part. We didn't have to do any math, okay? So now the question becomes, well, what is the concentration of OH minus? And how do we find that? Let's use our equation for Kw. Remember, Kw equals the concentration. I'm just going to plug in H plus here because that's what I wrote for mine, and I think that'll help you see. It could be H3O plus, same thing, OH minus. That's what Kw is. So we actually have this part, and do we know Kw? We do. So let's just plug those two values in and solve for OH minus. So it should be, I'm going to come down here. 1 times 10 to the minus 14 equals 0.1 molar times concentration of OH minus. So now we just cross divide. Cross divide both sides. This was our H plus concentration, remember. Cross divide both sides by 0.1 and 0.1. Cancels out over here. So now the problem is, and you're just going to plug this into your calculator, and I would put 1 times 10 to the negative 14 in parentheses and divide that by 0.1. And I got that concentration of OH minus equals 1 times 10 to the minus 13. And the concentration is units of molarity. Okay, any question? What questions? Can you go over that, all that again, please? Yes, I can. We're going to do another one with a base. We're going to do the same problem, but with a base in just a second. So recap on what we just did. We wanted to know, what are the concentrations of H plus and OH minus? That was the question in this problem. And it says we have a solution of 0.1 molar HCl. HCl, the first thing you need to always ask yourself when you're given some kind of acid-based problem is you need to say, wait a minute, is this a strong acid or a weak acid? It's going to help to identify that. You always go up to that table of strong or weak acids and you say, is it strong or weak? If it's strong, then that's going to make this a whole lot easier. Okay, strong means it 100% disassociates into H plus and Cl minus. So we said, okay, if we initially have 0.1 molar, which is what the problem told us, that was the concentration, and I have 0 of these things starting out. Well, when the reaction's done, so what's happened if it's weak? That's when we use Ka and we would solve. And we'll work a problem like that. I don't know if we'll get to it today, but for sure on Thursday we'll come back and work a weak acid problem. But for the time being, just to finish this problem, when we're done, we'll have 0 HCl. It'll all be disassociated. So we'll have 0.1 molar and 0.1 molar of our products, because every time you make one, you make the other. So the concentrations are identical. And because we now know H plus is 0.1 molar, we actually answered half of the problem just by understanding it's a strong acid. So we said the concentration of H plus is, well, it's 0.1 molar. So now we're just solving for the other part. What is the concentration of the hydroxide ion, OH minus? Okay, and to solve for that, we're going to use Kw. Okay, anytime you're asked questions like this, what is the concentration of hydronium? What is the concentration of OH minus? What is your concentration of H plus? Well, if it's a strong acid, you're just going to plug these things into Kw. And up here, we defined Kw. We said it's a numerical value at 25 degrees Celsius. I guess I should have written at 25 degrees Celsius so that you know you can use Kw. So you're just going to plug this value in, 1 times 10 to the minus 14, and we're going to plug this value in, which was 0.1. And then we're going to solve for this guy. And that's what we did. We just cross-divided both sides by 0.1 to solve for the concentration of OH minus.
Okay, I have a question.
Yeah.
So, like you said, at 25 degrees Celsius, Like, will you like give us problems, or will there ever be a time where that's not okay?
Nope. Nope. You'll always be at 20. You can always use KW. Yep. Don't even worry about that. Okay, now what are the same question here. What are the concentrations of hydrogen? Did that help, Aaliyah, by the way? Did
Yes,
that? Okay. Same question here. What are the concentrations of H plus? And what are the concentrations of OH minus in a 0.1 molar NaOH solution? What kind of solution is this? What is NaOH? Does anybody remember? Sometimes I wonder if my back hurts because of my posture in this chair. I'm always like leaned forward. So I try to sit up straight. It's a base, Kathleen said. It is a base, and in fact, it is the strongest base we know, because in solution, this dissociates into the cation and the anion. And OH minus is our strong base. So in solution, NaOH is a strong base. It's going to break apart into Na plus OH minus. And we can write the same kind of initial final concentration thing we did up here. We can do the same thing. Initially, we have 0.1 molar, and 0 of these things are products. But finally, when everything's done, we have 0 NaOH left. We have 0.1 molar of the sodium ions and 0.1 molar of the hydroxide ions. So we already answered half the problem. Here is our concentration of OH minus, hydroxide ions. So now we're just going to answer the other part. What is the concentration of H plus? Well, if we know the concentration of one, we can always find the concentration of the other using Kw. And we'll just plug in our value for Kw. This time we'll plug in the value for OH minus. So remember, Kw equals concentration of H plus or H3O plus, same thing, OH minus. So we'll just plug the number in. 1 times 10 to the minus 14. That is the value, and that never changes, the constant value for Kw. You can always plug that value in. And then we are solving for H plus this time because we know the concentration of OH minus. Oh, and I just wrote OH minus. I meant to write 0.1 molar. Same math here. You're going to cross divide by 0.1. In the units here, some of you may be wondering, well, what about units? Because like you don't have a unit on K, but you do on molarity. K is a unitless value, but we always have units of molarity on H plus, or any ion or any substance where we're finding concentration, it will be units of molarity. Unless I specifically say what is the percent solution, like in chapter 9, we talked about mass volume percent. And then we talked about molarity too. If I ask you what is the mass volume percent, then you would tell me, oh, it's this percent. But otherwise, if I say what's the concentration, anytime the word concentration is in there, it's units of molarity every time. All right, so here, same math. So that means the concentration of H plus is the same number we got earlier, 1 times 10 to the minus 13, molarity, molar. Okay, so now you see why I say chapter 10 is kind of reminds us of chapter 7. We're starting to get into the thick of some things. So, all right, we've done all this work with water, and we spent all this time talking about water for a reason, okay? Because of this, this helps us characterize whether a solution is acidic, basic, or neutral. And that is very significant, okay? Our body is made up of all kinds of solutions that are slightly acidic, but we ingest things as well that are slightly basic, different medications. And so we have to know how these things collide together and how they work together. And we have to be able to classify something as acidic, basic, or neutral. Because we want things that have a constant steady pH in our body to maintain that. So how do we define this? What are our parameters? Well, a solution is considered acidic, basic, or neutral based on these concentrations that are present. Now we know in pure water, the concentrations are right here, 1 times 10 to the minus 7. And what kind of pH does water have, pure water? It has a acidic, basic, or neutral. Anyone? Water is neutral. So guess what? If the concentrations of our ions are 1 times 10 to the minus 7 or right there by it, that's a neutral solution, all right? However, we're going to start with defining acidic. It is acidic if the concentration of H plus deviates from this number in what way? Well, if it's greater than 1 times 10 to the minus 7, H plus, and if the concentration of OH minus is less than 1 times 10 to the minus 7 molar. That is now classified as an acidic solution. While it's neutral if the concentration of H plus is equal to 1 times 10 to the minus 7. We already knew that. And the concentration of OH minus is the same, equal to 1 times 10 to the minus 7. And guess what? It's basic if the concentration of H plus is less than 1 times 10 to the minus 7, and the concentration of OH minus is greater than 1 times 10 to the minus 7. Okay? So essentially it's acidic if you have more H plus, and it's basic if you have more OH minus. Hydroxide, OH minus, makes things basic, the more of it you have. Hydronides make things more acidic and therefore by nature more corrosive. And always remember, if we know the concentration of one, H plus, or OH minus, we can always find the concentration of the other using Kw. Okay, this right here. Now, this is a whole lot to memorize, and these numbers are really teeny tiny. So we are going to walk through an easier way to classify something if it's acidic, basic, or neutral, but this is the foundation of pH. This is where pH is developed from, okay? So you need to know that. All right, here's a question. Milk has a H plus concentration of 4.5 times 10 to the minus 7 molar. Is it acidic, basic, or neutral? What's the concentration of OH minus? So what do y'all think? Is milk acidic, basic, or neutral? Based on what we said right up here, I'm going to leave that visible. Is OH minus supposed to be the same for acids and bases? Seth, what do you mean? Like the concentration is the same for acids and bases? No. Like for usually a solution that is acidic, the concentration of OH minus is very low or very little. For something that's basic, the concentration of OH minus would be a lot higher. Does that answer your question, Seth? Oh, thank you. I have a typo. That's supposed to be greater than. There we go. Appreciate that. Yeah, that was a mistake. This is if it's greater. I said greater than and I wrote less than. All right, so Abby says that milk is basic. Okay, so let's look at this. We know we have this value 1 times 10 to the minus 7. First, let's compare 4 times 10 to the minus 7 to 1 times 10 to the minus 7. Well, this is 4.5 times 10 to the minus 7 is greater than 1 times 10 to the minus 7, right? That's a bigger number. 4.5 is bigger than 1. So because of that, actually falls right here, where H plus is greater, the concentration, this is our concentration of H plus. So we are saying that the concentration of H plus is greater than 1 times 10 to the minus 7 here. So that means milk is acidic. We don't think of milk as being acidic, but it is slightly acidic. Now, what is the concentration of OH minus? Well, let's just plug this value into Kw and solve for that. We know 1.0 times 10 to the minus 14, that is Kw, and that equals our concentration of H plus, which is just 4.5 times 10 to the minus 7 times concentration of OH minus, which is what we're solving for here. So we're going to cross divide 4.5 times 10 to the minus 7 on both sides. And it will cancel out over here. I'll mark through that in black. It cancels out over here. So now to solve for the concentration of OH minus, put this in parentheses. 1 times 10 to the minus 14 divided by, especially put this in parentheses. When I'm grading exams, if you read my feedback, by the way, everybody should be able to see that I typically, unless you get a problem 100% correct, I will try to type personalized feedback, customized feedback on your exams. And several times I will say for certain people, you set everything up right, but your value was not quite right, your final answer. Maybe it was a calculator error. And here's the most common calculator error is people will forget to put things in denominator. When there's a multiplication sign in your denominator, you've got to put it all in parentheses. Okay. So what did y'all get for the concentration of OH minus? Anybody do it? Well, I can do it. 1 times 10 to the negative 14 divided by, okay, Jenna said she got 2.22 times 10 to the minus 22. Oh, Lord, it's not going to, got to the minus 8. Yeah, Jenna, double check that minus 22. I'm counting 1, 2, 3, 4, 5, 6, 7 zeros and then a 2. So I think it should be 2.2. I can't see decimals after that, but times 10 to the minus 8. Okay, good. All right. Oh, I have a meme for you guys. Did I already show y'all this one? Tell me if I did. I like to show this when we get close to the end of the semester. Does anybody feel like this? Start off strong, right? I don't know why this face right here just gets me every time. At least they're still smiling. Are you still smiling? Me. And then start off strong. Look at all the shading. And you're like, well, I'll just draw a little stick for you. And then by here, we're just hanging by a stick over here. That's one of my favorite end of semester memes. So if you feel like that, that means we're close to the end. Okay. We're close to the end. Hang in there. You can do it. We're almost there. So, all right. Water. We discussed water, all of that H plus OH minus stuff just to get here. And I better plug my computer in or I'm going to magically disappear. pH scale. So pH is a whole big unit. So if I could kind of break our chapter up into different units, we have labeling, defining acids and bases, conjugates, the strength of acids and bases, understanding that, difference between strong and weak, understanding KW and water. So that's 4 things that we've covered. pH is another one, and buffers is what we're getting to at the end. So there's 6 big topics here, and we are on, I guess, 5 of the 6. So pH scale. I'm going to just read this slide first. It says the amounts of H plus and OH minus in aqueous solutions, just meaning in water, are relatively small, and it becomes awkward to use molarity, okay? These 1 times 10 to the minus 7, 1 times 10 to the minus 8, they make my head hurt. In fact, here's an example of how much it makes my head hurt. Which number is larger, 1 times 10 to the minus 7 or 1 times 10 to the minus 8? I look at that and I'm like, I don't know. I have to think about it, right? You really have to think about it. 7 is a smaller number, but a negative 7 this one's larger than 1 times 10 to the minus 8. So all that's just confusing. The whole point is just, it gets hard to use these really small numbers and negative exponents. So that's where the pH scale comes in. And we're gonna learn to use nice round whole numbers. You can have a decimal in pH scale, but most of the time it's with whole numbers. And that's why we use the pH scale, because it's just easier to look at and make a judgment on whether something is acidic, basic, or neutral by the pH scale. So first off, when we're talking about pH, we have a P in here. What does the P stand for? P is a function. It is a mathematical function, and you don't have to know exactly how this works, but you do need to know what it stands for. It means you take the negative log. So everybody look at your calculator. If you have a cell phone, you might have to turn it sideways, and you should see a log button on there. And you should actually have used this in a math class before here, okay? You should be familiar with the log button on your calculator. Now, when you use the log button in this class, you always need to make sure you put a negative in front of it, the negative log, okay, of whatever value, okay? So that's what P stands for, the negative of anything. So if we have pH, that means the H here is standing for the concentration of H+. That is a big deal in acids and base worlds. Okay, so if we have pH, what we're saying is we're going to take the negative log, we're going to do a mathematical function on the concentration of H+. That is pH. I don't know if I'm going to give you this equation on your resources page. I might. You will need this equation for exam 4. You'll need it a lot. Okay, pH is the negative log of H+. Guess what? We could take P of OH. What is the P of OH? Can you write the definition for that? It is the negative log of the concentration of hydroxide. Okay. All right, we'll come back to those in just a second. So we're going to look at these values down here, the following concentrations of H+, acidic, basic, or neutral, and now we're going to calculate what is the pH. So you can use your calculator to do this, but if we have a solution that the H+ concentration is 1 × 10⁻⁷, we said that is what kind of a solution? Acidic, basic, or neutral? Neutral. Now, what is the pH? Okay, so we're just going to do pH equals the negative log of 1 × 10⁻⁷. We're just going to plug that in. So go to your calculator and you'll do negative log of 10⁻⁷. What did you get? 7. Okay, why don't you go ahead, everybody take a minute, do the next 2. You ask yourself, is this acidic, basic, or neutral? And then calculate the pH. All right, anybody have an answer for this second one, number 2? Is it acidic, basic, or neutral? Basic, basic, basic. Okay, concentration of H+ is less than 1 × 10⁻⁷. What's the pH? Should have done negative log of 1 × 10⁻⁹. And y'all got a pH of 9. Okay, what about the last one? Number 3, Allison says acidic. And your pH equals what? Okay, y'all are all getting the same thing. Good, 1 × 10⁻⁴. Anybody notice a trend here? Tia noticed it before I could even say. Tia, you could teach the chapter on acids and bases. She noticed a pattern. Yes, there's a pattern here. If your base number is 1, then whatever your exponent is, this is your pH. Now, positive, the absolute value of that, okay? Yeah, I think that's what Jenna means, opposite of the exponent. Aaliyah, what is your question?
So I'm confused. Well, maybe I wrote it down wrong, but so acidic, the H+ isn't greater than 1.10⁻⁷?
Yes, yes. Now, I know you're thinking, well, 9 is greater than 7. But on the negative scale, negative 9 is less than negative 7.
Okay, maybe that's why I was confused.
It's the negative thing. And that's why I did this whole thing up here about saying which one's larger. It's awkward when you're dealing with negative exponents. But a -4 is greater than a -7. -9 is less than -7. It's that negative scale. We don't often deal with the negative scale. Does that help?
Yes, ma'am.
Okay. All right, so yes, there's a pattern here. If your base number is 1, okay, if your base number is not 1, then you can't apply this pattern. But if it is 1, then you shouldn't even have to calculate it, right? You can just say, oh, that's my pH. It's what the exponent is. Here's the pattern. So if H plus is 1 times 10 to the minus, whatever that number is, we just call it Y here, then pH equals Y, okay? Now notice it's not pH equals negative Y. It's just Y, okay? Not negative Y. So now, instead of saying, well, if my H plus concentration is greater than blah, 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 or blah, 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 now we can just say pH is neutral if it's 7, it's acidic if it's less than 7, and it's greater if it's basic if it's larger than 7. That's so much easier, right? So much easier way to define things. Here's some pH scales and how these things relate. Okay, we actually did milk earlier, right? We calculated is milk acidic or not, and it's slightly acidic. Slightly, it's just barely smaller. The pH is barely less than 7. But if you just look at this, it gives you lots of different items, things we contact with every day. How much of you take in, some acidic black coffee? And we know a lot of this stuff, lemon juice, citric acid, things like that. Those are very acidic. Ammonia, different things we can use for cleaning our house. Those are basic. But essentially what the right side of the arrow is telling you is the pH value, the whole number. And what the left side of the arrow is telling you is the concentration of H3O. And remember, this is the same as the concentration of H plus and how that corresponds. Now you can pretend there's a 1.0, okay, here, but it's just telling you the exponent portion, the scientific notation portion, but it'd be 1 times that, 1 times that. They just didn't write the 1, which is okay. It's the same value, okay? So there's how these things relate. So if I ever gave you a question, I said, oh, your H plus concentration is 2 times 10 to the minus 5. You could come down in here and you would immediately know that you're somewhere around this pH. You could come look at this arrow and say, okay, if my H plus is in the left-hand column, I'm somewhere in this pH range, okay? Like say I gave you a multiple choice question. I said, here's your concentration of H plus, what's the pH? You could look at what's the closest answer, and you may not even have to throw anything into your calculator. It's kind of a quick way to judge your answer options according to this scale. All right, so these actually, I hope these are useful images and figures for you to determine that, okay? This other one on the far right-hand side, this over here, is just showing you how the concentration of OH minus and H plus relate to one another. They're inversely related. If one increases, the other decreases. Why? Why does that happen? Well, that happens because the multiplication of these two things equals a constant. A constant value. KW is a constant. So if one goes up, the other has to go down to keep the constant. All right? So that's why if we have 10 to the minus 13 over here, we have 10 to the minus 1 here. Notice the exponents add up to what? Every time, 12 and 2, 11 and 3. The exponents add up to 14. They add up to 14. So when you're dealing with these things, keep that in mind. Or remember how earlier we talked about pH and POH? There's one other equation I want to give you that's kind of a quick, handy little resource. pH plus POH equals 14. All right? So different people have different preferences. If I'm asking you questions like this, what's the concentration of OH minus? Here's your pH or whatever. You can use this equation, or you can solve for it using KW. There's two things. These equations kind of operate along similar lines, and you'll find you can arrive at the same answer often using pH plus POH equals 14. Or KW equals the concentration of H plus and OH minus. Okay, so these are two equations I would be familiar with. All right, any questions so far on pH? All right, I really want to get to these practice problems. We have a little bit of time left. I think we'll get there. All right, so I've been talking about if your base number is 1. But what if the concentration is not 1 times 10 to the minus whatever your exponent is? What if it's 2 times 10 to the minus y? Guess what my answer is? Hey, you have a calculator. Put it in your calculator. right? Don't try to, you can make a judgment call if you want, but let's just throw it in our calculator. So what's the pH? Well, we'll just do the negative log of this value, 2.3 times 10 to the minus 6. All right, so Jenna got pH equals 5.64. Okay. And pH is unitless. You don't have to write a unit here. You just give me the number. Okay. All right, let's do some practice problems with pH. What is the pH of an acidic solution? Because it's not just handy to know concentrations of ions. Sometimes it is, but we work with acidic or basic solutions. So I'm going to frame it this way. What is the pH of a solution of HCl? Okay, that solution contains 1 times 10 to the minus 6 molar HCl. That's the concentration of HCl. Is it acidic, basic, or neutral? You need to apply the same thinking we did earlier. HCl we know is strong. It's a strong acid. So if you start off with 1 times 10 to the minus 6 molar, when it dissociates, you get H plus and Cl minus. So initially you have 0 of these things. Well, when you're done, you have none of that, no HCl left, and all products. So guess what? My concentration of H plus equals 1 times 10 to the minus 6. And what did we say? There's a shortcut here. Our base number is 1. So what is our pH? It is the exponent in this case. So it's just 6. But if it wasn't, you just throw that in your calculator. You do negative log of 1 times 10 to the minus 6. And that will give you pH 6. Okay, but now let's change the game, change the number. What if you have 4.5 times 10 to the minus 4? Same steps here, same acid. I mean, I could tell you HNO3 or H2SO4 or H3PO4, any of those strong acids. You do the same style of thinking here. So we immediately can define the H plus concentration. I'm not going to write out the dissociation reaction like I did in the previous problem because it's the same thing here. When that is done, disassociating, the concentration of H plus is 4.5 times 10 to the minus 4. And from this, we get pH because pH equals the negative log of the concentration of H plus. So we're just going to plug that value in. And Jenna got 3.35. Is that what you got? That's what you should do in your calculator. So pH equals, and she said that you got 3.35. And that makes sense. Or if I didn't even ask you what the pH is, if I just said which one's more acidic, you could simply look at these two values and say, for which one do I have a greater or larger concentration of H plus? The one that is more acidic is the one that has a greater concentration of H plus. And this exponent, 10 to the minus 4, is a larger number than 10 to the minus 6. 10 to the minus 6 is smaller, okay? So this one is more acidic. Okay, if I said which one's more corrosive, well, the more acid content you have, the more corrosive a solution is. Okay, so this one would also be more corrosive. All right. Okay, now let's apply the same thinking, but there's a trick here. This one has an extra step. What is the pH? Notice I'm asking the pH, not the pOH. What is the pH for a concentration or a solution that has 1 times 10 to the minus 3 molar KOH? This is a base, and I'm asking you what is the pH. So we have an extra step here. We're approaching it from the other viewpoint. We're going to calculate the concentration of OH minus because that is what KOH will do. It's a strong base. So we have KOH, and it will completely dissociate into K plus and OH minus. So if we have 1 times 10 to the minus 3 starting out, at the end we'll have 0 of those starting out. we'll end up with 1 times 10 to the minus 3 of both of these things. Because this reaction is complete, gives you all products. So our concentration of OH minus is 1 times 10 to the minus 3. Okay, you have 2 routes you can go here. Remember how I gave you both of these equations earlier? I'm going to come back. I said you can use POH and pH equals 14, or you can use KW. You can do either one here. I don't know if I'll take the time to work both, but we can say, okay, negative log of 1 times 10 to the minus 3 equals POH. Then, once we get that, we could say 14 minus POH equals pH. All I did is I took this equation, 14 equals pH plus POH, and I just subtracted off POH from both sides. That's so pH in this case is going to give you 14 minus POH, okay? So you can use that route, or knowing the concentration of OH minus, we can go this route. We could say KW equals the concentration of H plus, plug that in, times 1 times 10 to the minus 3, solve for H plus, plug in KW, and then take the negative log of that, and you'll get pH that way too. I'm going to go back to my original route. I'm going to do that one. Sorry if I just erased that too quick. So what is the negative log of 1 times 10 to the minus 3? Well, it's 3. There's a shortcut there because our base number is 1. So you really don't have to do any math here. So POH equals 3, and then 14 minus 3 should give you a pH of 11. Okay, so pH equals 11. Oh, wait, sorry. Yeah, 14 minus 3, 11. Okay, questions there? All right. Now, what if, let's work this inside and out, okay? That way you really know. What if we are given the pH and we want to know the concentration of H plus? And this is important sometimes. We're going to talk about our blood buffer system on Thursday. So this is actually important for many reasons. Well, we have to undo the equation. We have to undo the log function. How in the world do we do that? There's 2 steps. I put this YouTube video in case you want to go watch it. It walks you through step by step. I think it's a great little outside tool. If I don't explain it well to you, watch that video and it's very short, a couple minutes. All right, how do we do this? First thing we do is we're going to take this equation, we're going to move the minus sign over. So we're just going to say negative pH equals the log of H plus. We got to undo the minus. If it's true that positive pH equals the negative log of H plus, then the negative pH equals the log of H plus. Now we're going to take what we call the anti-log. Anti-log is a base 10, and we're going to move whatever our number is up into the exponent. So the log of H plus becomes the exponent. We're going to do it to both sides of the equation. That's how math works. If you do it to one side, you got to do the other. So we're going to say 10 of negative pH. We're just going to make this our exponent. Raise it all to the exponent. Equals the 10 raised to the power of log of H plus. And guess what? When we do that, this is an anti-log. Raising something to the exponent with a base of 10, that undoes the log. Takes it away. So now we have 10 raised to the power of negative pH is equal to the concentration of H plus. Again, the video walks you through this step by step. So if I ever ask you to say, here's a pH, your pH is 8, what's the concentration of H plus? We can find that. It's on the next slide. If pH is a solution of 8, what is concentration of H plus? So 10 to the negative, I'm going to plug in pH right here, negative 8 equals concentration of H plus. So it would be essentially 1 times 10 to the negative 8. All right, what if pH has a decimal though? We really don't like decimals in exponents, okay? So throw this in your calculator. You would just do 10 to the negative, if pH is 4.5, you do 10 to the negative 4.5 equals the concentration of H plus. But put it in your calculator because we do not like to leave decimals in the exponent position. Let me know what y'all get. Okay, Jen said she got 3.26 times 10 to the negative 5. Okay. Okay. Abby got 3.16 times 10 to the minus 5. Oh, Jenna says 16. Okay. 3.16. Thank you. Okay, do the next one. If pH is 12.3, what is the concentration of OH minus? We're going to have an extra step here. We've been solving for H plus. Well, pH is still going to give you, if we do 10 to the negative 12.3, that is going to be the concentration of H plus. So if you want, you can do it this way, but then you got to take this and plug it into the value, the KW equation. You can say KW equals H plus times OH minus, and you can solve for OH minus this way. Or if you do a simple step on the front end, do 14 minus 12.3. Because remember, 14 equals pH minus, or sorry, plus POH. So we'll just take a second and say minus pH, minus pH. Okay, now 14 minus pH equals POH. We'll make this easier. So if we do that, what do we get? We get 1.7. Should get 1.7. And that is POH. So now if we just do 10 to the negative 1.7, we'll get the concentration of OH minus. So you can do it two ways. Remember, KW, or you can use this equation, 14 equals pH plus POH. So the concentration of OH minus, either way you go about it, you should get, Jenna says she got, and Abby says she got 2.0 times 10 to the minus 2 molar. If you did use KW, you would plug in the 1 times 10 to the minus 14. And you would end up dividing that by the concentration of H plus. Okay, you would want to put this in your calculator first, get this value, and then do 1 times 10 to the minus 14 divided by that number, and that would give you the concentration of OH minus. Or you can do what we did, 14 minus pH gives you POH, and then you do 10 to the negative POH gives you concentration of OH minus. Questions there? This is a lot, guys. So if you're feeling a little overwhelmed, take a deep breath. You're going to practice this on the homework, and I'm going to give you a list of textbook problems that I recommend for practice before the exam. I really wanted to get to this problem because after that, we're done. We're at buffers. Let me do this last. I've got 5 minutes left. Hang with me. We're almost done. I'm going to bring up one more idea about pH scale to help you just understand it fully. pH is logarithmic. Okay, we said that. What does that mean? Well, if pH is increased from 6 to 7, how does that affect my H plus concentration? H plus concentration decreases from 1 times 10 to the minus 6 to 1 times 10 to the minus 7. This number is smaller. So it's a decrease. Okay. That is 10 times less H plus because look, our exponent is different by 1. Okay. 10 to the minus 6, 10 to the minus 7, that's a difference of 1 decimal place. So that's 10 times less H plus. So if it increases one whole unit value, you have 10 times less the amount of H plus. So what that means is a 1 unit pH change results in a 10-fold H plus ion change. The concentration of your ion changes 10-fold, decreases. I should say, well, guess what? A 2 pH unit change, if you go from, say, if you went from 6 to 8, results in a 100-fold ion concentration change from 6 to 8. So what is the result of a 3 pH unit change? That would be a 1,000-fold H plus change. Sorry, that's probably hard to read. Okay, so just to give you some context there, what I want you to draw from this, here's a very handy relationship that you can use on the exam. As you increase in pH, as you climb up the pH scale, you will decrease in H+. As you climb up the pH scale from 6 to 7 to 8 to 9 towards 14, you reduce the amount of H+ you have. These things are inversely related. The higher your pH, the lower your concentration of H+, the higher your concentration of OH-. Vice versa, as you decrease in pH, you increase the amount of H+. H+, the more of it you have, the more acidic something is, and lower pH numbers correspond to acidic solutions. I'm going to say that again. The more H+ you have, the more acidic that solution is. And it's the lower numbers on the pH scale. Anything below 7, 6, 5, 4, 3, 2, 1, that is an acidic pH. Okay, so remember these relationships. I will put this problem on a review because we're pretty much at time and I don't want to hold you guys over. So I'm going to put this problem on review for exam 4, and we'll look at it, and feel free to look at it for yourself. It's a really interesting problem regarding pH of our blood, and you could fall into a condition called